8 people, 9 now, okay. So we just need to check that you can hear me. So if someone could just say something in the chat, say yes or no. I suppose if I don't hear anything, it means I'm not being recorded. Yes, okay, great, fine. Stuck on the creaky chair. Right, so let's kick off where we were. So at the last lecture we had a bit of an introduction to what we were going to do, and then we started looking at effectively a bit of revision in amplifiers and things like that. And we've looked at a little bit of long tail pair work and some of the ideal characteristics. And then I sort of said there was going to be some non-ideal characteristics, and we sort of stopped at that point. So we think we talked about this a little bit. But non-ideal op-amps, one of the characteristics we haven't talked about with op-amps is that in an ideal one, if you put 0 volts into it, or 0 volts differential inputs into it, you'd expect to get 0 out of it. And because things are never perfect, you'll never get completely 0, you'll get some little offset. And so these are the things that we're interested in. Effectively, if you're putting 0 in, you don't get 0 out, and the question is why? Why do we not get that? As I said, it's down to all the transistors not being identical, even though they've been made on the same process, on the same bit of silicon at the same time, in the same conditions and everything else. They're getting very good these days. They used to be a lot worse than this. And this output voltage is due to two parameters. One is due to input offset voltage, which we'll talk about in a minute, and the other is due to input bias currents being imbalanced as well. So if I just change to that now, you're fed up with seeing me, I'm sure. So input offset voltage is due to imbalances within the device itself when it was actually made, so tolerances just not being quite right. It used to be the case, and it still is the case in certain conditions, where you can balance this out, and so op-amps will have an extra couple of terminals on them which allow you to put a resistor between it, and then you can use this to balance the resistor. And I think you probably did this in the second year lab in the design exercise. And that actually sort of offsets, gets you inside the middle of the chip and allows you to play with the offsets inside there. Input offset voltage can be modelled in a simulation, usually by including a voltage source connected to one of the inputs, and we'll look at that in a minute, how we can model these things and see the overall effect of it. Okay, because when you model op-amps, what tends to happen is that the op-amp model does not usually include input offset voltage imbalances, but will include input bias offsets. So the devil's in the details, so you always have to check the model you're using to see which offsets it's modelling or not. So input bias current is due to imbalance in the bias currents. If you think back to the long tail pair and the two transistors are in parallel to each other, they need bias currents to flow through them, and ideally they'd be identical. They've got to come from somewhere, and they tend to come in through they have to come in through the input connections. And if there's an imbalance in those currents, that leads to a voltage appearing in the system, and that then gets amplified and leads you to an output. So let's just have a look, because what's going on here. So we're going to simulate one now. So here's a 741. So we've taken SPICE simulation. We've got a 741 amplifier. So we've downloaded that model from one of the many vendors of 741s, and that includes a typical input offset bias inside the triangle in terms of the modelling. But doesn't actually include the input offset voltage bias. So we model that by adding in a 1 millivolt voltage source here. And as expected, when you configure this as a gain of 1, so this is a amplifier with a gain of 1, you would expect, with the input effectively grounded through here, so there's no input coming in, you'd expect the output to be 0, but when you actually run the simulation, you see it comes out at 2.8 millivolts. So we've got a 2.8 millivolt offset just for doing nothing in this op amp. Okay, so this is 2.9, 2.8 and a little bit. And remember, this is for a 0 input, so this is not ideal. And it's obviously got something to do with this 1 millivolt source that we've arbitrarily bolted onto it. But it's also got to do with the bias current offsets, which are modelled inside this op amp here. So is this important? Well, sometimes it is and sometimes it isn't. So in this case, if we unground the input and we now put a signal source in here, so we've got a 1 millivolt sine wave coming in here, 5 kilohertz or so, into the well, that's not 5, that's 5 hertz rather than 5 kilohertz. Coming through here, we can now see that we would expect that it have a gain of about 1, and we would expect 1 millivolt output. And true enough, we've got our 1 millivolt output variation, or plus or minus 1 millivolt, but it's superimposed onto a 2.8 millivolt offset. So the offset in this case is bigger than the signal we're interested in, which might be a problem. Put a bigger signal in, so here we are putting plus or minus 1 volt signal in. It's not a problem at all, because a 2.8 millivolt offset is so small that we're really not going to worry about it. But if we're trying to look at very small signals, these offsets can be a big problem, particularly if we start to put more gain in the system. So what are the effects of the input bias currents? So remember, we had a 1 millivolt source here. We take that out and we just build what would be an ideal amplifier with a gain of 1, and then have a look at what the output is for 0 volts input, and we can see that we're getting 0.8 of a millivolt out. So 0.8 of a millivolt is a lot less than 2.9 millivolts, so the majority of the offset is coming from the 1 millivolt input from inside the chip, which we modelled with a battery on the outside. But this is just typical. So remember, this is not fixed. This will vary anywhere between 0.8 and minus 0.8, depending on which chip you've chosen out of the box and what temperature and all kinds of things like that. So this is just a snapshot of a particular typical value. So we've got an offset of about 0.8 of a millivolt or so. If we now add a balancing resistor of what value? What, 5K, which is the parallel combination of this one and this one, and we put the resistor here, that allows us to actually balance this, and it's a very common way of doing that. So if we just model this system now with a balancing resistor in place, you can see now that the offset is now down to very close to 0. If both bias currents would have been identical, then it would reduce to absolutely 0, but they're never identical, so you never see that. So this is sometimes, so the difference between the bias currents is sometimes called the input offset current, and you can see for a 741 it's about 20 nanoamps, so it's not huge. And the new improved 741A, it's only about 3 nanoamps, and there are bigger improvements in that. So really, bias currents, pick the right op amp, bias currents should be not that important, but there will obviously always be outlier cases where it is important, so you need to remember about it. So all these offsets can be calculated easily. Well, I say easily. There's one equation that allows you to calculate the effect of all these offsets on your circuit. The output voltage is given by this bit that you're interested in, V in, and some gain, A being the open loop gain of the amplifier. So we can calculate what that is. That's the bit we're interested in. And then there's the gain due to the input bias current, and then there's the gain due to the offset voltage inside the chip itself. And so you can actually calculate what these are from your system. We used to do this in the first year and develop this. I think I've taken it out recently, so it'd be an exercise where you just sit down and work out where these characteristics are coming from. But it's not a hard thing to do. Right, but there is still a bigger problem with bias currents, because you might be forgiven to be thinking maybe I can just ignore bias currents if it's only 3 nanoamps and causing me very little offset. The problem is, and let's have a look at an example here. We've got a amplifier system positive gain amplifier, putting in the signal, running it through, and we're getting what we expect out, amplified version of the input, which is all great. In this case here, we've capacitively coupled, so it's exactly the same circuit, and we've just put a capacitive coupling in here to maybe DC block or something, and suddenly the output is very much different from what we expected, and we're only getting half of it, and it's all a bit offset as well. And all we've done is AC couple it, and the problem that we've done, because AC coupling is obviously, you know, a very common thing to want to do, but in this case what we've done is we've blocked any kind of DC bias current being allowed into the positive terminal. Remember, this positive terminal is connected to one side of that differential input long tail pair, so there's a transistor on the end of this, it's base, and it wants to have some current just to bias itself. It's got to take that current from somewhere, and that current has to come from the source. It can't come from the source in this case because this capacitor is blocking it, so there's no biasing on half of that long tail pair, and so all the biasing inside the op amp is then all over the place, and it doesn't work properly. Sometimes it's subtle, sometimes you can build a circuit like this and it can work for a few minutes, and then slowly the output will drift to in this case the negative supply, maybe the positive supply. It's completely random because of the bias conditions. The more bias current it needs, the quicker you'll see this effect, but they always need some bias current, and you couldn't build a circuit, you can test it for 5 minutes, it can work fine, but if you leave it for an hour it can be broken. So always think bias currents, how are they getting into my device, does it need them? In the first case, it's got a choice. It can take its bias currents on this negative input, it can take the bias currents from the output, there's a direct path through there, or it could even pull them out of ground, there's a direct path there as well. And the other problem that you can run into is something called slew rate. Excuse me. So the slew rate of an amplifier is a measure of its ability to output large voltages. It's a large voltage problem when the output is trying to swing between significant things. So in principle, an amplifier with a gain of 1000 can give us an output of 1 volt for a 1 millivolt input, so there's just a factor of 1000 between those two. It should also be able to give us 10 volts if we input 10 millivolts, because that's still just a gain of 1000. But although simple theory says that's within the range, it's still within the power supply, assuming we're running on plus or minus 15 volts, so that's not a problem. It might not be able to run its outputs fast enough to actually meet that. So in this case of a 741, we can run this simulation with different input amplitudes with the same kind of gain. We've got a gain of 10 or so on here. And you can see that as you increase the input signal, the output is a sine wave, and the black one, that's also a sine wave, and then as you're starting to get to the red one, it's starting to look a bit more like a triangle with a rounded top, and as you increase the input signal amplitude, you can start to see that it's starting to get like a triangle, and we're starting to get this linear region here, which is the output trying to move its output as fast as it can, but it's not allowed to move it any faster. The rate of change, volts per millisecond or microsecond, it's limited. So although, and that all becomes because if you take the rate of change of the sine wave, the maximum rate of change of the sine wave is just as it's going through this 0 point here, so this slope here. So the bigger you make the amplitude, the steeper this slope is, and so eventually this slope becomes steeper than the op amp can actually manage, and you get this distortion, which is called slew rate limiting. It's not a fundamental bandwidth limitation, because if you keep the input signal small, you can amplify those frequencies. It's an input magnitude problem, or rather an output magnitude problem. So you have to look on the op amp datasheet to see what maximum slew rate is and make sure that you don't exceed it. If that can be seen more clearly, and is a problem in fact when a square wave is used. So if we put in a 20 kHz square wave into our amplifier, a unity gain amplifier in this case, first case 1 volt, and the output is looking a bit like a square wave, but we've got a bit of a rise on the leading edge because it's being asked to swing its output very quickly. And the second, it's a 10 volt input, but it's been normalized so that we can fit it on the same graph, and you can see now that it's struggling to get near where it needs to get to, and we're turning it into a triangle. If you go higher in frequency and even higher in amplitude, you will probably find that the amplifier can't really move its output meaningfully at all in the time available, even though potentially its bandwidth says it should be able to. So that's something to watch out for. And if you're interested in being able to work out if your system is going to be slew rate limited or not, you can consider it by saying, well, the output voltage is going to be a sine wave with a gain factor built into it. So if we input sine omega t, the output will be a sine omega t, a being the gain of the amplifier. So the rate of change, if we differentiate that with respect to time, we end up with omega a cos omega t. There might be a sign change, I can't remember, my differentials may not be great. And so the maximum of that is occurs when this bit is equal to 1. So omega a equals 2 pi fa. Well, omega a is the same as saying 2 pi fa, so we can get f out of this. And that's the slew rate. And so as long as dV out by dt is less than the slew rate, which is that, we're going to be okay. So the slew rate has to be bigger than 2 pi fa. And f is the maximum frequency that you want to amplify, and a is the gain that you're expecting. So if the slew rate is bigger than that calculation, your amplifier is okay. You can obviously then fix your maximum output voltage. You must have a gain of 10. Then you can work out what's the maximum frequency that you can amplify. So that's all straightforward enough. Right, so there are other output limitations, drive limitations. Op amps can only supply a certain amount of current, and this is usually very low, tens of milliamps or so, which limits the size of a load that can be driven. You can't drive things that are expecting large amounts of current, so you can't drive very low impedance loads. So, for example, if you operate on a 10 volt supply and your op amp can only supply 10 milliamps of current at the output, you can't drive less than a kilo ohm of load, so 100 ohms would be no good. And even this will be starting to load the output. And this is a real subtle one, rail issues. And by rail I mean the supply. What's the maximum supply, and how close can your output voltage get, or your input voltage get, to the supply. So the output voltage on your op amp may not be specified to the supply rail. That means the output may not be able to go all the way to the maximum voltage you think it might. So as an example for 741 again, if you operated on plus and minus 15 volt supplies, if you look at the data sheet, you will it will only specify the output to be up to plus or minus 12 volts, so 3 volts difference. So if you then operate your 741 on a 5 volt supply, you're still going to lose 3 volts. So that means that your output can only go between plus and minus 2 volts, and that might not be enough if you're trying to drive logic or something like that. So some op amps are specified as rail to rail op amps, which means that their outputs can get very close to the supply. So if you operated them on a 5 volt supply, the output could go up to 5 volts, and it could go down to 0 as well, because that's important. Or sometimes you'll see them advertised as single supply op amps, which means that the negative supply will go down to 0, but the positive supply, your output may not get up to the 5 volts. It might only get to say 4 volts, but at least it goes down to 0. So these are things to consider when doing mixed signal systems. That op amps, they're good, but they're not brilliant. And once you start wanting to use the whole dynamic range, which means all of the supply, you can run into some issues. We also talked about infinite speed and bandwidth. So ideal op amps have infinite bandwidth. Obviously in the real world we don't have that, and we will have seen earlier that op amps start to actually fall away at a few tens of hertz in terms of their frequency response. We also have to worry about negative feedback, because they need to be operated in negative feedback mode, and we'll talk about negative feedback shortly. So we have to make sure that the criteria for negative or stability is maintained. So we don't want positive feedback, probably not, because that turns these things into oscillators, and we'll talk about that for a bit later on in the course as well. So in an op-amp, because they tend to be inverting, we need to maintain a phase shift around the loop of less than about 180, well, less than 180 degrees, and we also need to make sure that if it does go outside of 180 degrees, then the loop gain is less than 1. Otherwise, we're in a condition where we can support oscillation, and we don't want that. And the problem is that as a signal propagates through the op-amp, there will be a certain amount of delay. It's going to take time to go through the op-amp, and that means that you will see a phase shift from input to output, because that's the nature of a delay. It manifests itself as a phase shift in an AC system. As the frequency increases, the delay may stay the same, but the phase shift will increase because it will be a bigger fraction of a complete cycle. And eventually you could get to the point where you've got 180 degrees of phase shift at a certain frequency. And that's where the op-amp has to roll its gain off, so that you don't get a gain of 1 in the feedback, or gain bigger than 1 in the feedback, because that leads to oscillation. So we start to get an idea that with the feedback system then we need to be able to distinguish the various criteria that we're interested in, such as the open loop response, the closed loop response, and the loop gain. And they've all got the word loop in, which tends to make it a bit confusing. They're difficult to distinguish between them, particularly if you don't use them every day. And it's the loop gain that we're interested in for stability. Closed loop gain gives us the overall gain of the system, but the loop gain is the thing that affects the stability, and we can manipulate this potentially to give us improved response. Right, so it's probably worth having a quick look at this to see what I'm talking about, because it's a lot of words. Let's put a bit of maths in the way. So most op-amps are compensated to give a single dominant pole, and this means their frequency response rolls away with frequency. And dare I write with a pen? Let's see if I can do that. So you end up with a response that starts off with high gain and then rolls away with frequency. Okay, so this is defining what's going on with that single pole transfer function, and this is where the pole is, the point where it starts to change direction. And we can define that in many different ways, but it's just a time constant times s, where s is the Laplace operator, and we would normally replace it with j omega for steady state response. Now, it'd be nice to know where this pole frequency is, but it's not normally specified on data sheets, but it's quite low. For a 741 it's about 10 Hertz. So at 10 Hertz this gain is starting to fall away, but remember this gain here is 200,000 or so. So it's got a long way to fall before the gain is low. And when this being a log graph, when it crosses this axis here, this is 0 dBs, which is a gain of 1. So this is the unity gain frequency where it crosses this axis. And unity gain frequency is sometimes called FT, and it allows us, and that's the thing that is specified on the data sheet, and with a bit of analysis of this equation and understanding this graph, we can work backwards from the unity gain frequency given in the data sheet to work out what the pole frequency actually is. And there's a little bit of maths here that explains that, straightforward enough, but basically we're just turning the equation round to work out what omega naught would be, given that we know the unity gain frequency and the open loop gain. So if you want to look at that, that's how you do it. So given this, you can calculate this. But also we know single pole, so this is 20 dBs per decade anyway, so we can take a shortcut, just put a ruler on a graph and run a line up. So this will be the response then for a typical op-amp such as a 741, and you can see, well, this one's rolling off about 5 Hertz on this log graph. As I said on the previous slide, this is a slope of 20 dBs per decade because it's a single pole system, and this is the open loop gain response, which looks like about 90 dBs or so in this case. The other thing about these responses is that we are used to looking at the amplitude response, but there's also a phase response, and the phase response is really interesting when you start to look at things like stability. So every time there's a pole you get a phase shift of 90 degrees. So in this case there's a pole here, and you can see that there's a phase shift of 90 degrees, and at the pole frequency it's shifted by 45 degrees. So we've got notionally 0 degrees of phase at 0 frequency. It drops off. We've got 90 degrees of phase throughout most of the operating range of this system. And we would expect, having looked at this graph, to say that this graph should go flat across here, but the graph is actually dropping down. So what that's telling us is there is another pole at 1 megahertz or shortly around it, which is causing this to go down to then at 40 dBs per decade. But they don't show you this in the datasheet graph. So that could be an issue, because then you're starting above these frequencies, just starting to get to 180 degrees of shift, which we know is a bad thing for stability. However, because the gain has dropped away so much, it's never going to be bigger than 1 when the phase has got down to 180 degrees. So this system, this op-amp, will be pretty difficult to make unstable. This other pole in here is caused by other poles within the op-amp itself and parasitics and stuff like that. So this pole here is the one that's introduced by that little capacitor inside the op-amp, and it's designed to be put there so that these other ones that occur high up don't actually have an impact on the stability of the system. So this is called dominant pole compensation, so you might come across this in various control options as well. So just as a reminder on the basic feedback systems, so we understand what these different loop gains really mean. For a basic negative feedback amplifier, there are several gains that need to be defined. So we've got A, which is the open loop gain of your op-amp, which is your 100,000, your 200,000 or so, which is too big to be useful on its own. We then have some feedback applied to it, and we have this thing called a feedback factor, which is B, which is usually the ratio of resistors in the case of op-amps. And the loop gain, which means if you go around the loop in a circle, what do we see? Well, we go through a gain of A, and then we go through a gain of B. So AB is the loop gain, which you go around the loop. So the closed loop gain is the transfer function of this whole system, with the feedback applied and all this. And if you can go through the analysis, I'm sure you've done it loads and loads of times, you end up with the this quite famous equation where the output voltage of the closed loop system is A over 1 plus AB. So it's A over 1 plus A times the feedback factor, or A over 1 plus the loop gain. And then if A is very large, when we like A to be infinite, we can start to look at this and say, if A is very, very large, then 1 plus AB approaches AB, so we can get rid of the 1, and that leaves us with A over AB, and then we can cancel out the A's, and it leaves us with 1 over B. So the closed loop system becomes defined only by the feedback factor, and we don't care what the value of A is, as long as A is very, very large. And that's the real nature of of feedback. So thus this whole complicated system with millions of transistors, a huge gain and everything that goes with it, and instabilities and all these things not being the same, no two amplifiers are the same, doesn't matter if you apply feedback to it, because the whole function of this system is defined by B, which is the ratio normally of two resistors, or resistor and a capacitor, or whatever, the feedback factor. And that's the key to feedback. So when we look at these graphs, we can actually tell a little bit more about stability as well by looking at this. We would be used maybe to looking at open loop responses and saying, okay, because I understand about gain bandwidth products and stuff, I can understand that if I control the gain to be, say, 40 dBs, gain of 100 or so, then I can put a line on here, and where it hits the open loop response, that will be my overall response. So at that point I can say that I've got a frequency response where I've got a gain of 40 dBs up to 10k. And likewise, if I dropped it down to 20 dBs, I'd get a wider bandwidth response. And that's what we would normally look at for this. But what we can also look at on these graphs, certainly for straightforward amplifiers anyway, is above the red line, above our gain line, what's going on here. And that actually is the loop gain. So we could measure from here to here, and that would tell us what the loop gain is. So this bit here starts to become very useful for analysing stability, because remember, the loop gain has to be less than 1 for stability. So that's what we sort of like. So we can actually sort of ignore this part of the graph, take that bit at the top and say, let's look at that in terms of stability. So let's do that. So if we had an amplifier that had this type of response, so we've got another pole in here dropping away, we can see that if we had a gain of 1 or gain bigger than 1, and then we looked at the phase response here, we can see the phase response is getting to be bigger than 180 degrees, which means if we had a feedback amplifier we'd end up with it being very unstable. If we had a gain higher than that, 40 dBs, and then look down, we can see the phase shift is at that point is less than 180 degrees, so we'd be okay. So actually this is running into problems for a low gain amplifier, and you might think that's counterintuitive, that you'd have problems with a high gain amplifier, not a low gain amplifier. So there's a certain amount of counterintuity here, but the problem with fast systems is if the gain is closed loop gain is too low, you can run into problems. Right, nothing else to say about that, I don't think so. That's what we're looking for. Where's the gain bigger than 1, and what's the phase shift at that point? Or where's the phase shift become 180 degrees, and is the gain bigger than 1? So a gain of 1 here, remember 0 dBs is a gain of 1. At that point here we're dropping down and we're much more than 180 degrees, so we'd be unstable if we built a buffer out of this circuit. So, as I've just alluded to, you can reduce the loop gain, which increases the stability by increasing the closed loop gain. So this is our closed loop gain line, for example. The loop gain is there, and at that point there we can drop a line down and see what phase we've got, and that tells us how well we're doing. And if we're above 180 degrees, then we're stable, and how far we're above 180 degrees at that point is called the phase margin. It's number of degrees, so it's just a measure of how far away we are from an instability in the system. Likewise, we can actually measure a gain margin, which is saying at what point does it become 180 degrees in terms of gain, and what gain are we operating at, which is the green line. We take the difference between it, and that's the gain margin. That's how much spare gain we've got to play with in our system before it becomes unstable. And you want to have a bit of gain margin because not all amplifiers are the same, and these poles can move around a little bit as well. Right, so that's how we can improve the stability of our system a little bit. But why we want to do this? Between these two op amps, so I said the two op amps, one is the op amp that's got this uncompensated response, and the other one is the one we just looked at, the 741, which had a falling away at 10, so we've got a lower gain response. If we were to design for a gain of 40 dB, so a gain of 100, in this compensated case, we would get a maximum gain of, in the compensated case, the one with the roll-off at 10 Hz, we get a maximum bandwidth of 10 kHz, which is what we spotted on the previous slide. But if we use this uncompensated amplifier and still run it with the same gain of 40 dBs, we would actually increase our bandwidth to over 20 kHz. So by using an uncompensated amplifier, we can improve the bandwidth at the expense of low gain performance. So as long as we don't build a low gain amplifier, we'll be okay. But a lot of people want to build low gain amplifiers, which is why these compensation poles are built in to make it easy for people, so you don't have to worry about gain margins and phase margins all the time. But I'm sure as engineers leaving Southampton you want to know about such things, because you might be able to manipulate it to your advantage, because you've gained a doubling of the bandwidth by understanding that if I have an amplifier that's a bit lively, I can get a better response out of it, and it can still be perfectly safe to use. It's quite interesting stuff, really. So voltage feedback amplifiers, we've done a bit on those, and you're probably very familiar with those. You probably haven't come across current feedback amplifiers before. Says they're a bit different, but they achieve the same results. They're still gains, but instead of resulting to instead of responding to voltages going in, they respond to currents, which means they tend to be low impedance inputs rather than high impedance inputs. So it's a little bit different from what we would normally expect, and they're quite good for amplifying current signals, sort of optical signals and things like that. So voltage feedback, an ideal model would be infinite input impedance, and we just measure the difference between these two inputs and it gets amplified. In a current feedback amplifier, we've effectively got a very low input impedance between these things, and the output voltage is the current multiplied by some transfer impedance. which is calculated from the circuit parameters. But in an ideal situation, these come up with the same output answer going forward. So I've taken this from a data sheet. If people are interested in understanding this in a bit more detail, this is actually quite a good source to look at. So TI, Texas Instruments, this this web link here will get you to an analysis. But basically, they look very similar circuits. We've still got two resistors in this configuration here. Everything still holds. You can run basic nodal analysis through this system, and you end up with the same output answer for output voltage against input voltage, remember. So you get the same answer coming out, but it's a slightly different way of doing it, and there's slightly different performance between the two. And what you can actually do if you look into these in some detail is that you can separate the gain and the bandwidth from each other. So a current feedback amplifier, the gain and the bandwidth can be independent of each other, whereas with a voltage amplifier, the gain and the bandwidth tend to depend on each other. These are normally unity gain stable as well, and there are conditions that are required to maintain the stability of these things. But we shouldn't worry too much about that. But basically, if you want low noise systems at high speed, then you should consider current feedback amplifiers. Voltage feedback amplifiers can be perfectly good as well, but voltage feedback amplifiers are much easier to work with and give good performance in most cases. But just be aware that current feedback amplifiers exist and can be very useful. Right, so the use of these amplifiers, now we've got over the basics of them. Voltages is what's normally we would consider amplifying with these things, which is very common, although depending on what signals coming in, there can be currents and even charges, which are non-moving currents, which need to be amplified as well, and different amplifiers can be used to achieve these kind of results. So we should be familiar with voltage amplifiers. We've got inverting amplifiers and non-inverting amplifiers, and they're used in negative feedback configurations, and we've done a fair amount on negative feedback now. So just for completeness, the non-inverting amplifier looks like this. We've got input coming in. The interesting thing here is the input impedance is very, very high, almost infinite if you've got a good amplifier, and the gain is set by the ratio or relationship between these two resistors here. You can run through the basic analysis. This is a straightforward way of doing it, and it shows that effectively that the gain of this is going to be 1 plus R1 plus R2, R1 over R2, and the gain will roll off after omega t, the unity gain frequency. So this part of the expression here has a frequency term in it, which will eventually become significant. But this is the main gain function, and this is the frequency dependence function of this system. Now the inverting amplifier is even simpler. In this case, the gain is given by R1 over R2, and there's a phase inversion which gives us a negative sign. There are various different ways of analysing this. You can do it by virtual alert approach, which you probably did in the first year, or you can do it by a superposition approach by suppressing this voltage, treating this as a voltage source, suppressing it, treating this as a voltage source, suppressing it, working out what's going on, adding the two together. If you do that, you get this kind of expression here, which leads us effectively back to our sort of feedback function. And as G tends to infinity, which is the gain of the circuit in this case, you end up with everything cancelling out, and you get R2 over R1. But this should be very familiar to everyone, so we won't labour the point there. So amplifiers for use as a current source. Now this is where it starts to get a bit more interesting. Some transducers are essentially current sources. So an important example of this is a photodiode, which generates a current, which we call a photocurrent, when light falls on it. So when light falls on your diode, generates a current. and fundamentally it's a current that's generated. We can turn it into a voltage, but it's the current that we're interested in. We would like to amplify that, and normally we would want to present that output as a voltage, so we need some kind of current to voltage converter, and the simplest current to voltage converter is a resistor. So the straightforward approach is to say, I've got this current source here, I'm going to put the current it generates through a resistor, and that resistance will cause a voltage to be generated across it, and then I will use an amplifier, in this case a non-inverting amplifier, to amplify that voltage seen there, and that gives me the voltage output. And that seems like a very straightforward and sensible approach. This is the small signal equivalent. We've got a current source, so we're assuming a sort of an AC signal coming in here. Got a current source which is generating the photocurrent. That current is then amplified through this amplifier system, and we get the output voltage. Now, you will have spotted that there is a capacitance that has appeared from nowhere in here, and this is the junction capacitance of the photodiode. As light falls on this, AC light is falling on here. Remember, there's a junction in the photodiode, and that is a depletion zone, so it acts a bit like a capacitance, and it takes a while to fill up and empty with the change in polarity of the light falling on it. And so we model that as a capacitance. So now we've got a capacitance that has to be charged and discharged, as well as the voltage being measured across this resistor, and so we've got this RL system, which is a time constant, which means it's going to take time to charge up and get to the final voltage. Also, if there's a cable between our photodiode and our input, that can look like a capacitance as well. So this capacitance here could actually be due to a cable that's connecting our photodiode to our amplifier. And so we'd be interested to know what the effect of this capacitance actually is on the performance of our circuit. So as I alluded to, there's a time constant involved, and if you get time constants you tend to end up with poles and things being affected by frequency. So RL and CS tend to form a time constant, and that leads us to a bandwidth which is 1 over RL CS. And if the capacitance is 20 picofarads and our resistor is 10 meg or so, this leads to a cutoff frequency of around about kilohertz or so, which is not great. So given that we don't know the value of this capacitance here, you can model it. So here we go, here's a SPICE model, here's our amplifier, we've got a 741 in there, so we know that it's going to be good for about a megahertz or so on a good day. We've got a current source, and we've got our 10 meg resistor, and we've got our capacitance, which in this case we're saying we don't know what it is, we'll turn it into a parameter, and we're going to step this parameter x, which is the value of the capacitance, through these three values here, which we put into a list. So this is telling SPICE to step this parameter x in the list of 10 picofarads, 20 picofarads and 100 picofarads. So it's going to run the simulation 3 times with these 3 different values for the value of capacitance in here, and we're going to run it from 100 to however many noughts that is, looks like a megahertz. And this is what you get. So you get flat response, which is what you expect, and then as you increase the capacitance, the frequency at which it falls away starts to really drop off, and here you can see we're at a kilohertz or so. So that's not great. So what that means is, although it works and we amplify our light current, its upper frequency is controlled by the amount of capacitance on the input, this thing here. And this depends on many things, including the length of the cable and what type of diode you used. So that limits our upper frequency response in a sort of unpredictable way in many ways. So this leads us to something called a transimpedance amplifier, which is a simple way of actually getting a much better response out of the system. So here we've got our photodiode connected, it's got currents coming in, it's generating a photocurrent. The current has to come from somewhere, so it's actually coming from round here and out. And what's going on is you've got a virtual ground here, so the op-amp is trying to keep these two inputs at the same value. And the only way it can do that is by adjusting its output voltage up and down. So it will adjust its output to match these to 0, which means that whatever the current is here is the current flowing through here, and it gets amplified by the value of this resistor effectively. So that's what's going on here. So V out is now going to be equal minus R times I. So we've actually taken an input current and we've multiplied by the value of the feedback resistor, and that gives us an output voltage. And because of the virtual ground, any capacitance that is here that we model in parallel is now shorted out because it's across this virtual ground. Remember, there's 0 volts between these two inputs if this thing is operating as a proper amplifier. So it doesn't matter what the value of capacitor is in this area here, it's actually short-circuited. So it doesn't get a chance to charge up, so it doesn't get a chance to influence the circuit performance. In this case, we can see that we get a very large gain, or conversion. It's not really a gain because it's converting a current to a voltage. And we get all the way up to a megahertz before it falls away. So we've used the entire response of this amplifier. And it's given us an excellent performance. And we don't care if there's a cable connecting here with capacitance, because the capacitance is shorted by the virtual ground. So that looks really good, doesn't it? We've gone from the previous one, which had a very poor performance, didn't get anywhere near a megahertz, but was maybe the naive approach of just using a voltage amplifier and turning the current into a voltage early, to a bit of thought about what's going on, a bit of an understanding of virtual grounds, and suddenly, with a very simple expedient of understanding what's going on, we've got a full response up to the megahertz or so of the op amp, and it doesn't matter what capacitance it is because the capacitance is effectively not in the circuit. It's really neat. So just to show what happens if you put in the capacitance, and what happens is it should have no effect because, as discussed, we've got a virtual ground here. So the voltage across this capacitor is always 0. What do the words say? Yep, so that's what we've just discussed. However, although a simple analysis says this should be great, which is just what I've been telling you, unfortunately we cannot assume that it will be perfect across all frequencies, because we know that the amplifier has its own frequency response, and at high frequencies it will be dangerous to assume that all is well, as a virtual ground approximation would start to fail and the input capacitance will come into play. Right, now that's an interesting point. So on the previous slide we didn't bother putting the capacitance in because we said it doesn't really exist as far as this ideal world is concerned, and look, we've got a fantastic response. In actual fact there is a capacitance here, but it's nulled out by the virtual ground. But the virtual ground requires a very high gain in this system to allow that virtual earth to happen. And we know that as frequency goes up, the gain of this system will fall off, and eventually the virtual ground will fail, which means that we can no longer assume that there's no volts across the capacitor, and it may well have an effect. So, what happens if we add in some input capacitance? So, assuming the amplifier is a single pole response amplifier, so open loop response will be given by this, and we've seen this a few times now and you've seen it in previous years. If you now apply Kirchhoff's current law to the VI node, this one here, you get this equation. So all the currents add up to 0. So you've got VICSS, this is the current here, you've got IS coming in, and you've got VI minus V0, which is difference across here, over RF, and they've got to add to 0 because what goes in must come out. And if you rearrange that, you end up with this. By then substituting in the open loop equation, you can rearrange that to get this response here, and then so the overall response of your system becomes, with a bit of just substitution and simplification, so V out over IS, output voltage over input current, is equal to this equation here, which has several terms in it, including an S squared term, an S term, and the bit that's probably the thing that we're interested in. But anything with an S squared and an S is a second order response. So fundamentally there's a second order response dependent on frequency, because S is a frequency term in this system, so it'd be quite interesting to know what's going on. So if we're allowed to assume that A0, which is the open loop gain of the amplifier, is infinite, then the solution will reduce to the simple analysis, okay, which will just boil down to probably RF. But unfortunately A0 is very large and is frequency dependent and sadly not infinite, so we would have to analyse this in a bit more detail to see what's going on. So Given that AO is very large, then the amplifier unity gain frequency, omega t, is A0 over tau, where tau is the time constant of the system. And then we can say that the poles are found at the denominator of the previous equation. So this one here, just take the denominator bit. Simplify that down and try and then match it to the standard second order term. So we've got Q, our Q factor, and our natural frequency, or resonant frequency. And with a bit more messing around of these equations and relating them to each other, so we're trying to work out what Q is and we're trying to work out what omega naught is by comparing it with the standard equation form. You can work out that omega naught is omega t, the unity gain function, over RFCS, and Q is approximately equal to RFCS omega t, if this applies. So it's not completely straightforward, and I've missed out a whole load of steps there. If you want the steps and you want to go and look at them a bit later, these are my steps that I would put in. So I would suggest at some point you try and go through these and understand how we've gone from one to the other, because this second order function is going to crop up quite a lot as we go forward. So the result of this, if we then include our capacitor and start to do some simulations, is that we end up with some peaking as this virtual ground starts to fail at given at certain frequencies, and the stability of the phase margins and the gain margins start to get a bit dodgy. So we end up with these peaks around the response. So we can see that it's quite good for these responses here for small amounts of capacitance, but as the capacitance goes up we start to end up with a lot of peaking response. And so this can become quite a violent thing. This is the damping response of your second order system. So this is where the Q factor comes into play. Okay, so the fact that the ideal equations tell us it's all going to be wonderful, a little bit more thought, adding the capacitance in and looking at what the whole equation is and identifying as a second order feature means that we would expect some kind of second order response, and that's what we're seeing as we vary the capacitance. The question then becomes is how do we calculate what the ideal capacitance is, and can we compensate for it? So we start to investigate that. If we fix our input capacitor as 20 picofarads for a given system, we've measured it and it said, well, it's actually 20 picofarads. And then we say, how do we compensate for this? Let's try putting some capacitance across this feedback resistor and see what happens. So here we're going to be varying this capacitance, this one here, between 0.01 picofarads, it's very small values, up to 5 picofarads or so, and see what happens, because this will have an effect on the frequency response of the system. And you can see that we start with, when we have very low capacitance, the peaking is there because it's not having much effect, and then as we increase the capacitance we can actually damp this peaking down and eventually get to a point where we've got rid of it completely, and in fact if we put too much in we start to lose our frequency response and the gain starts to fall away earlier than maybe it could do. So what we're probably interested in is either this, what's the value of the feedback capacitor for this green line, or possibly getting close to this blue line or somewhere in between, and that gives us the maximum flat response before it all starts to fall away. So what I'll do is I'll let you reflect upon that over the next few days or so, see if you can figure out the effect going on, because we've sort of rushed through that a little bit, and then what we're going to do in the next lecture is work out mathematically where we can fix in frequency our new compensation and what value of capacitance it's going to be, so how we can have control over what this shape looks like by understanding what's going on in this circuit in terms of the maths. It's a second order problem. I'm sure you've seen them all before, but you might not have seen them in this kind of configuration before. So at that point I think we'll stop because time's getting on. It's getting 5:02. I'm not sure if we're supposed to be 45 minutes or an hour in these lectures, so let's split the difference and stop now. I'll put this recording up on Blackboard, and at some point I'll put the slides up as well. I hope you found that interesting, and we'll pick that up whenever the next lecture is. I'm not sure when that is, but it's going to be Thursday, I think. Okay, so that's the end of it. Bye for now.